let's talk about homework 10, the design, verification, and documentation of a power supply and LED biasing circuit. Just to remind you, this kind of report is a formal report, and to use this checklist to make sure you got all the documentation issues taken care of. All right. I have a template just for this assignment. All right, that we'll talk about in a moment, that you have access to, but you're going to design a power supply with an input of 9 volts and an output of 5. That means you got to select R1 and 2. Now I've given a sample file, so the only values you can't choose are 100 and 300 ohms. I'd like you to do your own work. For reasons I'll explain later, you want to keep your R2 values less than 500. All right, and the diode biasing points are here. All right. Again, the template is already there. Same resources, so you don't have to go hunting for things. All right, but let's go through the report. So, title like normal, name, canvas, and yes, use the Google Doc way of turning things in like we did for homework 6. This seems to be working very well. Myself and the grader are able to provide feedback on what to fix, and you're able to fix it right away, so much faster than the Canvas environment. That whole system is how myself and fellow faculty write grants with each other, and we'll edit each other's work. Right, so we're working on teams just like we want you to work on teams. So abstract, pretty straightforward. There's the circuit. There's a link for you to download one, so you don't have to create it from scratch. However, you should make it from scratch just to make sure you know what you're doing and how to get things done. But to limit the frustration value, or levels, I should say, I give you the file. So here's the design. Now, the real design equation in the data sheet is here. All right. Now, if you select R2 small enough so that it's a lot less than the design voltage you're going for, right, you can leave out that part of the equation, and that's what I'm saying. All right. So then you just see me going through and finding R2. Now, the thing is we only have V out and we have 2 unknowns, R1 and R2. You have to choose something and then check to see if it worked. So I choose R2 or R1 to equal 100, right? I get 300, and then I check, yep, it's 5 volts. Then I do the I adjust times R2, which gives me 15 millivolts. Well, that's much less than the 5 volts we're going for, so it works. All right, then we design the LED driver, we write the loop equation, solve for R3, we substitute, and we just round up the value. All right, then I verify it, and I put everything in. I did add a node name here for some analysis later. And then I run it, and I highlight the important things. Now notice there's like this border here that I'm normally very critical of. The thing is it's kind of impossible to grab that nicely. So in this example, with DC operating points, you can have a little bit of border like that. All right. I even tell you that. Then I have the results and discussion. Well, we have our theoretical values and our simulated values, and I just calculated the relative error. Now the thing is that relative error is so small that were you to make the circuit, you could never detect it. The resistor tolerances would move things around, and the noise would make things a lot harder to measure than all those digits of precision from SPICE. But why isn't it exactly right from theoretical to simulation? Well, V in isn't exactly 9 volts. And you'd say, well, why? Well, there's a 0.1 series resistance, so the voltage in is not ideal. So you can see V in 8.99. Now that is so close to 9 that it's, hardly anything. Also, V reference is not always 1.25. In fact, with temperature it varies. In the simulation it's 1.24136. All right. Now I could calculate what things should be, but a slight difference caused by that in V out will cause VF to change, which then will cause IF to change exponentially. All right. Conclusions are pretty simple. Really, it's just one thing, the data sheet, right? And that would be it. So I would just make sure to give the TA and the instructor commenting privileges. I know a lot of you give editing privileges. That's okay. But, let's go through, right? This figure, you can read everything. There's no weird borders. Every component is black. All the dots are black, right? That figure's good to go. There's no transient in there for me to look at. But all the equations are right. Here, I'll just type it right here, right? There's no x's for multiply. There's